Maybe we have to start now. Hello, everybody. Today we have a great pleasure to listen the lecture by Hermann Nicolai. He will tell us about update of supermembrane theory. Okay, please, 1 hour.
Okay, thank you very much for this invitation to give this long distance colloquium seminar. Yes, so this is an update on supermembrane theory. It's mainly based on this paper which I wrote with Olaf Lechtenfeld just about a year ago. And there are also very specific papers that are relevant to this particular work, which I have cited here. I mean, it's always good to start out the lecture with the main message. And the message is the following. You all know about superstring theory, which is the theory of a one-dimensional extended object. And that's a theme that has dominated theoretical high-energy physics for some time now. But one can also worry about higher dimensional extended objects and their supersymmetry extension. And in particular, there's something called a brain scan, where one sort of makes a complete list of such theories, and especially the supersymmetric ones, which cannot be constructed in arbitrary dimensions. So in particular, there's a maximally supersymmetric such theory, which is the D equals 11 supermembrane theory. It was constructed already 35 years ago by Bergshofer, Seskin, and Townsend. And this is a uniquely distinguished theory. In particular, it contains 11-dimensional supergravity as a kind of low energy limit, or at least zero mass sector in the terminology of string theory. And being uniquely distinguished, it is a candidate, at least in my opinion, for non-perturbative unification of string theory, or what's called, so it's a real candidate for what's called M theory. And the message is that I will try to convince you of the virtues of this claim. Of course, the problem is that membrane theory is much harder than string theory, and I will explain why this is the case. And so the progress in this subject has been rather slow. So as I say here, I will try to explain some aspects and some of the difficulties with this theory, and try to convince you that not only that it is a major challenge of theoretical physics, but that it does deserve much further study. So if you have any questions concerning little particular points, then feel free to interrupt me. If it's longer questions about philosophy or whatever, then I would prefer if you ask these or keep these questions until the end. So let me start at the beginning. The relativistic p-brane is it's a generalization of the so-called Nambu-Goto theory, and it describes p-dimensional surface, or it's also called p-brane, that moves in some target space of higher dimension. Here you see x mu is the target space coordinate, and the dynamics of the theory is described by giving x of mu as a function of the membrane coordinates, which are, or the brane coordinates, which are sigma 1 to sigma p. And then there's also a time coordinate on the world volume of this p-brane. And then what you do is you simply compute the induced metric in this particular way, as it is given by this formula. And then you simply compute the Lagrangian is basically just the volume. I will here restrict attention to flat Minkowski background, but at this point, we could in principle still allow more general target space metrics, in particular curved target spaces. There's also a single dimensionful constant here that characterizes theory, which is this T sub P, which is the so-called membrane tension. There's no other dimensionful parameter in the theory. Now, an equivalent description of this is the so-called, many people refer to this as the Polyakov action, but it's really due to Brink, Di Vecchia, Howe, Desa, and Zumino, where you introduce the world volume metric, Gij, as an independent variable. And then the Lagrangian looks like this. What you can check, at least at the classical level, for the classical equations of motion, if you solve for this world volume metric in terms of the target space coordinates, the brain coordinates really, then you get back from this formulation to this. This is something that everybody knows. For string theory, it's of course crucial for the Polyakov approach to string theory. But at this level, this also works for higher dimensional p-branes. And you notice that there's also a cosmological term here, if you like, which is only absent in the case of string theory, strings being one-branes in this terminology. Now, I'm sure you also know that for string theory, we have a highly simplifying feature, namely the Nambu-Goto action, although it looks nonlinear. You can, for the Nambu-Goto action, you can choose a gauge such that the equations of motion become linear and effectively free field equations for the coordinate x mu as a function of the world volume coordinates. An equivalent description of this fact in connection with the Polyakov action is that you can use in 2 dimensions, you can use 2-dimensional diffeomorphisms and conformal symmetry to gauge away the world volume metric, this thing here. And then the gravitational path integral is reduced to a finite dimensional integral over the moduli of the world sheet. So that means that this makes an enormous simplification of the path integral, namely, on the one hand, the difficult part of the path integral, which is the gravitational piece of it, is a finite dimensional integral. And for the rest, you still have to do a path integral of these x mu coordinates, but that's a Gaussian theory, and we know how to do Gaussian integrals. Now, the main issue here is that for membranes, there's no such simplification for a p greater than 1. Because, for example, for membrane, metric already comes with 6 components, out of which you can gauge away 3, and then you're still left with the path integral. So that's the basis. This has been known for quite some time. People have also studied classical solutions of the membrane, and there are not that many. But we are interested in the supersymmetric extension of these theories. And as I said, there's a unique and maximally supersymmetric such theory where the target space dimension is d equals 11. And as I said, this was first formulated by Bergsof, Seskin, and Townsend 36 years ago. And as I said, and this is what I want to argue in my talk, this is a candidate theory for non-perturbative formulation of string theory. I should say that these theories, they're kinematically very constrained. They also exist in 4, 5, 7, but these theories are not of such, not the main interest here. And the result, which was also obtained by us a long time ago, is that this theory can be obtained as the n-to-infinity limit of a maximally supersymmetric SUN matrix theory. So this is another point I will explain. Now, as I said, progress has been slow because there remains the main unsolved problem, which is quantization. As I said, there's no gauge which linearizes the equation of motion, and therefore you're not talking about free field quantization as in string theory, but a fully interacting theory on the world volume, which means in particular that the determination of correlation functions cannot be reduced to free field theory computations, unlike for string theory. In particular, there's no membrane analog of the Veneziano formula, which that was the iconic formula that kicked off string theory. And in view of the nonlinearities of this theory, covariant quantization a la Polyakov is challenging. So at the moment, the only realistically feasible approach to that theory is the so-called light cone gauge quantization and in a flat Minkowskian background. Doing this in curved background is much more difficult. I mean, curved backgrounds are already a problem in string theory. But even if you restrict to this kind of targets, to this target space, and try to proceed, there remain difficulties which have not been resolved until today, or only partially resolved. One concerns the existence and properties of the n-to-infinity limit. Another way to phrase this is the question whether the theory is really renormalizable in some sense or not. There's the question that in the light cone gauge about target space Lorentz invariance. This is the well-known calculation in string theory when you reproduce that the target space for the bosonic string target space dimension must be equal to 26. There's been for the already classically to check Lorentz invariance, it's not so easy. The first one to do this was Goldstone back in 1980, but he never wrote up his results. And for the supermembrane, the matrix approach, we showed this back in 1990, that the finite n approximation breaks Lorentz invariance, and but such that classically Lorentz invariance is recovered in the n-to-infinity limit. The question is whether d equals 11 is the critical dimension of the supermembrane, in the same sense that d equals 10 is the critical dimension of the superstring. We have recently obtained some evidence, but I will not further talk about that because that's yet another aspect. And then there's the question of constructing vertex operators and with those eventually correlation functions. Now, my approach, or the approach I want to champion in this talk, is based on the fact that the supermembrane can be alternatively described as a one-dimensional supersymmetric gauge theory of area-preserving diffeomorphisms. This result about the matrix model is then simply can be reduced to the fact that the area-preserving diffeomorphisms can be approximated by SUN as you take n to infinity. And the aim will be not to get or remain stuck with the finite n approximation, but to deal directly with this gauge theory, because then this really amounts to studying the n to infinity limit of the theory. So here are some basics, and now I'm getting a little more technical. How to work out the light cone formulation of the theory. So as I said, we have target space coordinate x mu, which depend on, in this case now, 3 world volume coordinates, psi I or tau and sigma 1, sigma 2. And they're also fermionic coordinates. I will not say much about the fermions because they're just carried along, and they, of course, make life more complicated in terms of calculations. So I will just keep these terms, but not comment very much on them. So the way you now proceed is then you have a sort of generalized vielbein. It's a rectangular vielbein. The lower index runs over the world volume coordinates, and the upper index lives in the target space. And from this, so this is just what we had previously, plus a fermionic modification. So you calculate sort of generalized induced metric, which now also has fermionic contributions. And now, in order to simplify the action, you go to the light cone gauge. So x mu is split as follows into 2 longitudinal null coordinates, and in this case, 9 transverse coordinate xa. And then you identify the x plus coordinates with a membrane or world volume time coordinate in this way. So this is completely analogous what people do in light cone gauge string theory. And then you also have an accompanying condition for the fermions. Now with this, you can sort of work out what this EI mu is, and then you can also work out this induced metric. And what you find is that actually the equations simplify a bit, in the sense, if I now take the world volume metric and split it into space part, time part, and time space part, then this is what you get. In particular, for the space part, I just get this simple expression in terms of the transverse the target space coordinates. So are there any questions at this point, or? Okay, so I'll go on. And now we want to compute the metric determinant on the world volume, which is, of course, written here again. And then there's this simple, nice formula of the determinant of a 3x3 matrix. You can express it in terms of a 2x2 subdeterminant times an extra factor. This is what we have here. So we've split this into a piece containing the spatial metric determinant, which is G bar. And then another factor, which is written here, where the U was defined here. So this is still a rather complicated expression. And then we simply substitute this expression into the Lagrangian. So here again, we have the membrane tension. Here, this is the Nambu-Goto factor. And as I said, there's still a fermionic extension, which takes this particular form. I've said before that the membrane tension is the only parameter of the theory of mass dimension 3. And what you can now do in order to understand how this is related to the fundamental constants of string theory, for this you have to do what's called a double-dimensional reduction, where you compactify the target space dimension by one dimension, and at the same time you compactify the membrane coordinates by one, identifying the 11th target space coordinate with the second brane coordinate. So that's a real dimensional reduction. And in this case, you have one more parameter, which is the radius of the 10th compactified dimension, which spatial coordinate, which I call R10. And then you see here how these quantities are related to the constants that appear in string theory. You know that in string theory you have two fundamental parameters. One is the string coupling constant, and the other is the alpha prime parameter. And here you see this. So here the string tension, or this is the string tension, inverse alpha prime, is simply T3 times R10. So it has to be like this for dimensional reasons. And furthermore, the string coupling constant is dimensionless quantity, which is related to the 10th coordinate in this way. You may remember that Ed Witten at some point derived the results relating the radius of the 11th dimension to the string coupling constant, and this is exactly this relation, although it's here obtained in a slightly different way. So in this way, you can express the membrane tension as a function of the alpha prime of string theory and the string coupling constant. And now you can already see that this is going to be more complicated, because if you develop an expansion in T3, it sort of entangles the alpha prime expansion and the string coupling expansion, which are in string theory, they're completely different. You can study these expansions separately, but here they get intertwined. So next thing, in order to simplify or better understand the dynamics, one now goes to Hamiltonian description. And this canonical analysis for the bosonic membrane was done long ago by Goldstone and Hoppe in Jens Hoppe's thesis. And the analysis for the supermembrane is analogous, and I will not go into the details. This is explained also in the original paper by Bergsov, Seskin, Townsend, and also in our paper. of 1988. So you simply compute the canonical momenta, you compute canonical brackets. In this case, you also have to replace Poisson brackets by Dirac brackets, but that's just a technical aspect. And there's also the spatial diffeomorphism constraint, which is written here, which takes, I mean, many of these expressions have just analogs in string theory. So in string theory, the R would just assume one value, and this would just be P times X prime plus whatever else. And then you compute the Hamiltonian density, and then the Hamiltonian assumes a relatively simple form, and this in the light cone gauge, namely it's P squared, but just like a free particle. And here you have the membrane tension Q squared times the metric, spatial metric determinant. And in string theory, this would just be P squared plus X prime squared. So it would again be a well-known expression. But here, because it's a 2x2 determinant, it's really like a fourth order in X. So string theory would have P squared plus X squared, if you like, whereas this is like P squared plus X to the fourth. So it's more like an anharmonic oscillator. And again, there's fermionic contribution. And from this, again, like in string theory, you can compute the mass, well, operator only after quantization, but it's the classical expression for what would be the mass operator in the string theory. So you see, we have this P squared plus T squared G bar plus the fermionic contribution. Now, what about the zero modes? Because I said that the theory does or should contain 11-dimensional supergravity as a zero mass sector, and that's this can be seen as follows. Just like in string theory, the zero modes of the target space coordinate and also the fermions decouple. So you have this kind of free super algebra, which is written here. And this just concerns the zero modes. And for this, we know that the smallest representation is indeed 44 plus 84 bosons and 128 fermions, which is exactly the light cone content of 11-dimensional supergravity. 44 is the 11-dimensional graviton. 84 is the three-form field in light cone gauge. And then we have the gravitinos in this 128. So this is just the massless multiplet of d equals 11 supergravity. But we still have to fold in the wave function depending on the internal excitation of the membrane. So in order for the theory to actually would reproduce 11-dimensional supergravity as the zero mass sector, you have to show that there exists a normalizable wave function depending on the internal membrane coordinates that's annihilated by the mass operator. For the superstring, this is again rather trivial to solve because in that case, this ground state is simply the bosonic vacuum times the fermionic vacuum, where both are infinite products of harmonic oscillator states or supersymmetric harmonic oscillator states. So it's rather trivial. And you get the excited states and the discrete spectrum by applying the well-known way the bosonic and fermionic oscillators to this vacuum. So all of this is very well known to any string theorist. And this is what accounts for the very simple structure of the string spectrum and its factorization to left-moving and right-moving states, modulo this L equals L0 bar constraint. Unfortunately, life is not so simple with the supermembrane. And well, first of all, to this day, there's no rigorous proof that actually such a massless wave function exists, or an eigenfunction with eigenvalue m squared equals 0 exists. And furthermore, as was shown in this old paper and independently by Andres Milga, this operator m squared has a continuous spectrum starting at 0. So there are no excited one-particle excitations. And at first, when we first had obtained this result, we thought this was a disaster because it means that it would mean that the zero mass states are unstable if, for epsilon energy excitation, you are immediately in the continuum. So it would seem that that the theory is simply unstable. But as I will argue now, there's a different way. The more correct way to interpret the result is to say that the theory is not a first quantizable theory. So that means the thing that, the philosophy that we use in order to deal with the string theory, namely that you first quantize, then you obtain a discrete spectrum. And once you have first quantized, then you second quantize, going to something like string field theory. This is not possible. You right away into, you have, there is no such thing as a Fock space for the membrane, unless maybe you compactify. But if you compactify, then of course it looks a little bit different. So one really has to think about what this really means. As I said, the question concerning the existence of the normalizable ground state is not resolved yet, because this is not a simple product of fermionic and bosonic vacua, but a highly mixed state that involves all the states of the internal states of the membrane. So in order to now go to the matrix, let me see what time we have. Let me just say a few words about area preserving diffeomorphisms, because it turns out that this is a residual symmetry of the theory in the light cone gauge. In the analog of this in string theory is that the L0 minus L0 bar constraint, which says that the states should be invariant under shifts along the string coordinate. And this generalizes to the statement that the light cone description should be invariant under area preserving diffeomorphisms. Now, those are characterized by vector fields. Never mind this W, this is just a technical thing. Divergence-free vector fields are now in 2 dimensions. If a divergence-free vector field can be written like this, at least locally, and then the transformation, the coordinate transformation under area preserving diffeomorphism or scalar excitation can be rewritten in this way. And the nice thing about this expression is that it's like a Lie bracket. So you have D1A, D2B minus D2A minus D2A times D1B. So this is well known to be sort of Poisson kind of bracket. And it's easy to check that this actually satisfied all the requisite properties of a Lie bracket. And this, if you're thinking about functions on a 2-dimensional surface, this is actually the Lie bracket associated with the algebra of area preserving diffeomorphisms. Okay, the rest we don't, that's technical things, so let me not go into this. But now I will show you how the membrane theory gets reformulated as a APD, area preserving diffeomorphism gauge theories, and how that leads to the matrix model. One still has a residual gauge invariance, which is written here. And this has to be imposed as a constraint. And why is this for the consistency of the theory? This is because if you want, in string theory, once we fix the x, go to the light cone gauge, fixing the x plus coordinate, then you still have to solve for the x minus coordinate. In that case, in string theory, it's just x minus prime. You can simply integrate this because it's just one differential operator. But here we have 2 brane coordinates, d1, d2. So if you want to solve this equation for x minus, you have to satisfy an integrability constraint by heating this with another variable. And you can show that the integrability constraint is precisely this. So this is, as I said, this is the canonical generator of area preserving diffeomorphisms in this light cone formulation. Now, the other nice thing is that you can now rewrite the potential. This was the spatial metric determinant. Remember that GRS is DRX times DSX. And you can rewrite this for a 2x2 matrix. You can rewrite it in terms of this Lie bracket, which I showed here. This is really an elementary calculation. So now you have written this like Poisson bracket of two targets, transversal target space coordinates squared. And this means that the m squared can be equivalently obtained from a Lagrangian, which is where you have this the usual kinetic term, but now the metric determinant piece has been replaced by this funny Lie bracket squared. And you also introduce, because it's a gauge theory, you introduce ad hoc a gauge field called omega associated with this gauge invariance. And this is, I mean, this is where the relation appears with n equals 4 Yang-Mills theory, because when you do a dimensional reduction of supersymmetric Yang-Mills theory from 10 to 1 dimension, you have, of course, you also have the vector fields. If you go to the Coulomb gauge, then we're still left with, if you go light cone gauge, sorry, then you are left with 8 transverse components of the gauge fields, but then we need another one, which is this omega. And then you can check that this gets closer and closer to dimensional reduction of super Yang-Mills theory. Now, one further step here, and this was another insight that goes back to Goldstone and Hoppe, is actually that you can approximate the group of, or Lie algebra of area preserving diffeomorphisms by SUN. And what you do is you simply say, if you have a spherical membrane, you can expand any function on the brane in terms of spherical harmonics. So capital A would be like L and M with spherical harmonics. But in fact, this is even more general. You can also generalize this to tori and in fact, even higher dimensional, higher genus Riemann surfaces. And then you define the area preserving, the structure constants of this area preserving in this particular way, where again, you have here the APD bracket. And then they showed that actually this is nothing but you can represent with proper normalization, of course, you can reobtain the APD structure constant as a limit of the SUN structure constant as you take n to infinity. And then if you do this and then truncate to finite n, this is the Lagrangian you get. And this is nothing but the dimensional reduction of 10-dimensional Yang-Mills theory from 10 to 1 dimension. So if you like, this is the first example ever, I think, of gauge gravity correspondence, because we started out with the gravitational theory, the 11-dimensional supermembrane. We have now reformulated it in terms of a gauge theory, a Yang-Mills theory. So that this is what you get here. And now we have also used SO9 spinners, but that's again a technical point. Now, when you supplement this with the SUN gauge constraint, this is indeed the same, very same Lagrangian that underlies the M theory proposal that was made by BFSS many years later. Their picture is actually based on assuming D0 branes as the basic constituents of M theory. But we're really interested in the n to infinity limit. And in fact, I think it's just an interpretational difference, because if you really succeed in constructing or showing the existence of the n to infinity limit, you have nothing but the supermembrane. It's nothing but that. So as I said, the interpretation is that the supermembrane is not a first quantized theory. It's not a one particle theory like you would get when you first quantize when you start by first quantizing the string, but it's a fully non-perturbative description.
Excuse me, can I ask a question?
Yes?
If you don't have the first quantized membrane, how
Yeah.
do you get the 11-dimensional supergravity spectrum?
Well, this is what I showed before. Kinematically, you get it by looking at the zero modes. So the only unsolved problem is showing, still have to show that there's a normalizable ground state wave function for the m² operator, which depends on the internal membrane modes. Or rather, in this case now, we would simply take the Hamiltonian of the matrix model and look for zero mass eigenstate, and have to show that it is normalizable. It's square integrable function. So that, as I said, there's no direct proof of this. I mean, there are very good arguments to assume that it's really true, but so far there's no proof.
Okay, thank you. Another question.
Yeah.
What is the gauge group for the membrane? Is it SU infinity?
SU infinity being the same as APD, area preserving diffeomorphisms. So it's an infinite dimensional gauge group. So you're really talking about, I mean, one thing is to do the n to infinity limit of the matrix theory, but a more direct way of dealing with it is to simply take the theory with an infinite dimensional gauge group. And this, at least at the level of the Lagrangian, is completely well defined.
Thank you very much.
So let's see, for the rest, let me just skip this. Here, there's an argument to sort of reinforce my interpretation. This is taken from some lectures by Thibaut Damour. So what you see here is a diagram where here you have the mass eigenvalues. So here you see the discrete eigenstates of the string. And here you write this as a function of the string coupling constant. It's here called G². And what in fact, this is work of Damour and Veneziano. What they hypothesize, also in a slightly different context, I'm sort of reinterpreting their insights a bit, is as you switch, I mean, this is just free string theory, but once you switch on the string coupling, then these eigenmodes will split up into and have different mass eigenvalues. And the picture they have is a little bit like this, in the sense that you now have this for each massive state, and there's an exponentially grown number of them. You know, everything merges into a continuum as in the limit G infinity. And this again is in accord with this Witten observation that as you take the string coupling to infinity, it's like an extra dimension opening up. So that exactly fits with what we found for the membrane, in the sense that the 11-dimensional theory must have a continuous spectrum, so it precisely fits with this. So far it's just old results, review of old results, but here's a little bit of new results. Of course, the main goal is to evaluate correlators, and this is the subject of my talk, my work with Olaf Lechtenfeld. So what you would like to do is set up a path integral formulation for this theory. Of course, then you also have to introduce Fadeev-Popov ghosts and so on. You also have a ghost action to be included in the total action. So you have some kind of gauge fixing and Fadeev-Popov ghosts. So this is what you would like to compute. And this is also what you compute in string theory, but there, as I said, the really simplifying feature is that the exponential here is quadratic in the string coordinates. So we're really dealing with the Gaussian integral. Even if you look at more complicated Riemann circles, doesn't matter. It just means the two-point function gets more complicated. It certainly does, but it's still a Gaussian path integral, and this is about the only path integral kind of path integral that we can solve. So this our formulation tries to do this tries to do this in a somewhat different way by integrating out the fermions, because the theory is still quadratic in the fermions, also for the light cone formulation of the membrane. And then you get so-called Matthew-Salam or Matthew-Salam-Seiler determinant, which is for supersymmetric theory really a Pfaffian because you're dealing with real fermions. And this determinant has a simple form, so it's just a Fredholm-like form, so a unit operator, which is here, and then you have a certain integral kernel, which I've written here, and you have a fermion propagator, which in one dimension is basically just a step function, which you see here. It's just the usual epsilon step function, and so this is what it looks like for the matrix theory, and this is, well, this you don't have to look at the details of this because it would require more time to explain this. But anyway, you can also formulate this reformulate this integral for the APD gauge theory. Okay. Now, when you do this, actually, there is a subtlety, because if you have the bosonic membrane, when you do this, then there appear spurious infinities, because when you apply this, when you try to calculate this determinant using this log det equals trace log formula, there appear divergence factors of delta of 0, which make the determinant ill-defined. But at this point, and this is a really crucial point I would like you to retain from this seminar, is that this limit does not exist, or is unlikely to exist in the purely bosonic case. But what happens here is the following. We use my old result that you can sort of that there exists a linearizing transformation, a functional map, which is such that you can map the theory to a free theory in such a way that the Jacobian of this map is exactly equal to the Matthew-Salam-Seiler determinant, the fermionic determinant, times Fadeev-Popov. And it now turns out that if you just look at this map, actually the into infinity limit does exist, and this is what you get here. This is an expression that involves just the APD brackets. I've just written out the time coordinates on the brain, not the spatial coordinates, because that's implicit in this bracket notation. So you see that what you get here is a sort of sum of nested expressions that with nested APD brackets, which look like this, and we worked it out up to order g to the 6th, and becomes somewhat more complicated. But the crucial thing is that for this expression, the limit n to infinity does exist. So you can try to work with it directly. So that means, and this is the main message I want you to retain, that there is a divergence here, but that does cancel, or is divergence of one thing. The fermionic determinant is precisely absorbed by the divergence in the Jacobian, so that the total thing, in total, the limit for the path integral does exist. So there's no divergent factor. And by the way, this is the same problem for finite n, where the divergence appears as an independent factor that diverges as you take to infinity limit. So the conclusion of this is that for the supermembrane and for finite n, matching divergent factors keep the path integral measure well defined in the limit n to infinity, which indicates that actually the n to infinity limit does exist for the supermembrane. There's no such matching for the bosonic membrane, which indicates that n to infinity limit for the bosonic matrix model probably does not exist. And I remember that long ago, there was a question just for the bosonic membrane whether the theory is renormalizable or not. meaning actually that if you quantize, whether you would have to introduce counter terms of higher order, or whether just renormalizing the membrane tension would be enough. So it looks like this result can finally settle this question. And the answer is, or the conclusion from this is that very likely there is no quantum bosonic membrane. There's no end to infinity limit for the purely bosonic matrix model. Actually, these difficulties were already discussed long ago by George Savidi back in 1990. He has already some papers about issues with this, with how to take the limit and whether it might or might not exist. So, as I said, this is one of the main new results, namely that from this kind of argument you can now deduce that the 11-dimensional supermembrane, when you try to approximate it by an SEN matrix model, actually does have a well-defined end-to-infinity limit, but that's not true for the purely bosonic membrane or matrix model. Actually, in any dimension for the bosonic theory. Of course, for the super theory, you now have to cook up another argument to show that this only works in 11 target space dimension. But as I said, we have some recent paper where we do with Christoph Meissner, where we look at the kind of Polyakov formulation of the dimensional doubly dimensionally reduced membrane theory, and there we also find arguments that you have to target space dimension has to be 11. So taking it all together, it means the only supermembrane theory or membrane theory, quantum membrane theory that has a chance to exist is actually the D equals 11 supermembrane. The next thing is, I will skip this. This is also a technical thing that might eventually help. Now, finally, let me see. Yeah, I'm still within my time frame. Of course, eventually one would like to calculate correlators like you do in string theory for string scattering. And you would like to calculate, at least for the massless states, you would like to calculate scattering amplitudes. And from string theory, we know how to do this. You have these vertex operators. They go like e to the ikx. And then maybe there's some prefactor. But the e to the ikx is sort of combined. And then you can do that integral because again, it's a Gaussian integral. So I mean, this is old stuff, actually. It's not just Veneziano, but also Koba-Nielsen and this kind of formula that you find in every string textbook. So let me repeat that the reason it's so simple in string theory is it's always Gaussian integrals at the end of the day. This is not the case here because, first of all, as I said, it's a non-Gaussian theory. But secondly, one first has to come up with an analog of the string vertex operators. Now, what I show here is that this we have done such a construction back in 2000 with Jan Blevka and Arundhati Dasgupta, where we construct candidate expressions for the vertex operators for the emission of massless states from the membrane. But in view of this interpretational difficulties with a continuous spectrum, you would not expect there to be vertex operators for the excited states. We tried to look for them, but we did not succeed. So our failure may be interpreted as a confirmation that actually these things only exist for massless states. Now, this is tricky because such vertex, let me call them operators, or really talking about the classical analogs of them, they must satisfy stringent consistency requirements, namely, of course, world volume, target space, gauge invariance, supersymmetry. Also, they must reduce to the correct point particle limit. There was a paper by Green, Good, Perle, and Kwon already in 1999 where this has been constructed. But the most non-trivial check is that actually you have complicated expressions, but when you do the double dimensional reduction to recover string theory, then whatever the expression is, it must factorize into left and right moving states. And just to give you an example of this, the expression, we have expressions both for the graviton, a three-form field, and the gravitino. But for the graviton field, so here's one of the expressions that we found. So here is XA is again the transverse target space coordinate, 1 to 9. And HAB is the polarization for the graviton polarization. And then you see you get quite a few terms. So here's the usual e to the ikx. But as you see here, there's nothing like factorizing in this expression. But, and this is, as I said, the really non-trivial check. You now do the double dimensional reduction. It turns out that this quartic expression reduces to quadratic expression, which actually does factorize in the desired way. And the same is true of the other terms here, and as well as for the other vertex operators for that we have constructed. So in that paper, we actually did check that all the vertex operators that we have do obey this factorization once you perform the double dimensional reduction on the theory. This is one of the, you set k plus equal to 0 in order to avoid having to deal with exponentials of very nonlinear expressions. This is one of the dirty corners of string theory, because people sort of gloss over this point, because in order to make this happen, you somehow have to complexify the target space momenta. But this is a trick that's been well used in string theory. So as I said, we also have these expressions for longitudinal gravitons, gravitinos, and the three-form field of 11-dimensional supergravity. Now, the point is that up to this, at least up to now, nobody has been able to use these expressions for doing evaluating a correlator, because the path integral is just not a quadratic integral, it's very complicated. And so for this reason, no concrete expressions are available. You see, one reason why you can already anticipate that this is not going to be trivial. Here, we have the expansion as an expansion parameter. We just have the membrane tension. And if we take these, the fact which I told you about before, that the membrane tension is somehow expressible in terms of the string tension and the string coupling, you see that this expansion is something that intertwines alpha prime and string coupling expansion. So if you were able to do this, this calculation, you would learn something beyond merely either alpha prime expansion or string coupling expansion, but you would somehow reach beyond perturbation theory in some way, beyond what you get in the Veneziano formula. Because for the Veneziano formula, you would also have to start adding higher order corrections in order to make the thing unitary and so on. So you see, at least in a nutshell, that this difficulty reappears here, and therefore, but this is not for the future. We'd like to exploit the previous result in order to eventually tackle such a calculation. As I said, there are no analogs of massive superstring vertex operators. At least nobody has found any. Again, confirming probably that the supermembrane is not a first quantizable theory. But with this thing, you're right away in the non-perturbative regime. I sometimes compare this a little bit. If you think about QED, the way we learn QED, quantum field theories, that we set up Feynman path, Feynman integrals and Feynman diagrams to calculate scattering amplitudes and so on. But if you think about, if you were to treat QED in a sort of Hamiltonian approach, you would say, aha, I have to diagonalize the Schrödinger equation. So it's something like H psi equals E psi. And if you, I mean, of course, nobody's able to do this, but if you were able to do it just as a kind of Gedanken calculation, it would mean that, I mean, it would be clear that this eigenstate is nothing like a one electron state or one photon state or whatever, because we know that the electron is surrounded by an infinite cloud of virtual particles. So, and here this calculation, this Hamiltonian calculation, also with this wave function for the supermembrane, is somewhat analogous to what you would have to do in QED if you did a Hamiltonian approach with the functional Schrödinger equation. At this point, there are many further questions. This is why I said at the beginning, I wanted to argue or persuade you that the theory deserves much further study, although it won't be easy. So there are all kinds of questions. I've just listed 3 of them, but there are others. Anyway, so I'm now close to the end of my talk. I have 2 more transparencies. Now, one thing that's missing, and I've always thought, well, you know, what's the link here? The $1 million question is, if the 11-dimensional supermembrane is really candidate for M theory, where are all the dualities that we know from supergravity and superstring theory that are widely expected to play a key role in the non-perturbative formulation of string theory? And we're here we've just been talking about the M2 brane, but there's also such a thing as an M5 brane, which is associated. So M2 brane is coupled to the 3-form field. M5 brane would couple to the dual 6-form field. And then you can go on. There's something called the dual graviton, which is just related to the ordinary graviton, the way that A3 and A6 are related. And if you now think about exceptional symmetries that we believe to be there, there's actually an infinite tower of such objects. And you know, when I look at the string literature, it looks to me a little bit like botany, where you know have all these branes, D branes, M branes, Kaluza-Klein monopoles, and God knows what. It's a sort of very confusing array of objects with no classification whatsoever. So for the membrane theory, which I've been talking about, one must eventually understand how these objects can be accommodated into supermembrane theory. And maybe you need to go beyond supermembrane theory. That's also quite possible. So here's my outlook. Let me see. Yes, 5 o'clock sharp. So let me repeat what I said. Due to its uniqueness properties, the 11-dimensional supermembrane is a prime candidate for at least partial non-perturbable unification of M theory. I've tried to explain why it's much harder than string theory. And the other, and this was, I would say, our main result, is that the n to infinity limit is unlikely to exist for the quantized bosonic matrix model, but we have now indications that it may actually exist for the maximally supersymmetric supermembrane. And this is finally what we're interested in. We're not interested, at the end of the day, we don't want to do the theory for finite n matrix model. We really want to understand the n to infinity limit. So what's needed is an effort to develop more new computational tools to make the quantum supermembrane more computationally accessible. perhaps along the lines that I've sketched based on my work with Olaf, and by concentrating on quantities for which the APD expressions are completely well-defined. So that's it. Thank you very much for your attention.
Okay, thank you very much, Nicolai, for your very, very interesting talk. Questions, please.
Igor.
Okay, thank you very
Igor,
much.
please.
Thank you very much for a very nice talk. I have more questions concerning non-perturbative approach to superstring theory. Do you have in mind something like string field theory?
Have I in mind what?
Theory could be equivalent to membrane. Is it true or not?
A membrane is equivalent to what?
String field theory.
String field theory, yes. Actually, this is, let me see. This is a remark I skipped. A second. Yes, there's a way to, in fact, an argument along this direction. As I said, the theory has no massive excitations, but to recover string theory, you need to do this double-dimensional induction, as I said. And this corresponds to turning, pulling out a spike out of the membrane. This is visual kind of thing you do. But now if you have a membrane, you can pull out many spikes from it. And at each spike, you should recover one string Fock space. And in this sense, the supermembrane theory should contain something like a multi-string Fock space. So it should encompass what people are doing in string field theory, but in a way that is more sophisticated than simply than the way it's been done so far. But this idea I've had in my mind for a long time, but I haven't been able to do anything with it. But as I said, it's not implausible to me that this is actually what happens. That string field theory as is at this point, it's not. I'm not sure whether you agree with me on this, but I do not think it has really fulfilled the expectations in the sense that it now allows us to set up a non-perturbative scheme for superstring theory. It's technically extremely complicated, and just in order to recover scattering amplitudes, you have to work really hard. And I know that Ashok Sen is working on this, and Barton Zwieback has been working on this, but their results are very complicated. I'm not sure how far they've taken us.
Thank you very much. It's very interesting. I have another question. Do you think that consideration of gauge theory, like Young-Mills, for SU infinity gauge group could be useful for membranes?
Yes, in the sense that for me, SU infinity is nothing else but what I call APD. This is the thing. You have to take the limit in a very particular way. And then this was this Goldstone-Hopper result that you take, if you do this correctly, then you recover the APD structure constants by simply taking the into infinity limit of the SUN structure constants. And of course, you have to do the normalization in exactly the right way. Otherwise, it doesn't work.
Let me mention
the proposal is really, let's take this APD gauge theory from the outset and try to do it in such a way that whatever you do remains well-defined. Then you're dealing with the end-to-infinity theory right away.
Okay, some years ago with Irina Arefьева, we have shown that SU infinity gauge theory in 4 dimensions, it can be correctly defined. It should be quantized according to the Boltzmann quantization.
Okay.
So maybe after your talk, we should look again to this possible relation with membrane.
Yes. Yes, yes. Well, thanks for alerting me to this work of yours and Rina. But of course, keep in mind that the matrix membrane theory is in one dimension. We're not in 4 dimensions. But it doesn't exclude that you could apply these insights abstractly in studying SU infinity gauge theories in 4 dimensions. Yes.
Thank you. Thank you.
Please, more questions?
Maybe I will ask some question.
Oh, please, yes.
Well, thanks, Hermann, for your very interesting talk. I'm wondering if you will jump from SU infinity group to something like non-commutative U1 group. Will this somehow complicate or simplify possible computations?
If you go from commutative to non-commutative,
yes.
Not immediately clear to me. I would have to think about this question.
No, because I remember that we did some, let's say, compared to yours, very simple computation in non-commutative field series. And I remember that non-commutative U1 group was playing well generically.
Okay.
And in some sense, you can show some, it was some idea which was floating that the non-commutative U1 in some sense has similarity with SU infinity group. Actually, it was some discussion between Irina Arefьева, me, and other student of Irina, Dmitry Belov. We were discussing this particular thing. So I was wondering whether you consider at all non-commutative symmetry here.
Well, I haven't considered it so far. So this is a very interesting comment. But as I said, this last bullet point here is that, anything that can advance our ability to deal with these models is very welcome. So I would certainly encourage you to go on in this direction.
Okay, thank you.
Okay. More questions, please? Yes. Fiona Schibold, please ask your question.
Yeah, hello. Thanks for the nice talk. I had a question for superstrings in curved spaces. Sometimes those are analyzed in the uniform light cone gauge, where one of the light cone coordinate is matched with the worldsheet time, and the momentum of the other light cone coordinate, so the conjugate momentum, is set to a constant. Do you know if supermembranes have also been analyzed in such a
Well,
gauge?
if you go to curved background space, it's getting much more difficult. I mean, in some sense, already in string theory, because this maybe there's a way to do it for curved space, but or for very special curved backgrounds, but no, not for the membrane. The membrane, there are very few results on setting up supermembrane theory in curved space, and one of the few examples I know is work on ADS target space. So one question is, if I take the target space to be not Minkowskian but ADS, then you can set up. You can also try to look for a version of the matrix model, but it turns out that all the things I said about rewriting the membrane Hamiltonian in terms of these APD brackets, all of this has to be reconsidered, and I'm not sure whether it can actually be done, because in the expressions that I have, you will now have all over the place. You will have dependencies on the target space metric. So it's going to be rather involved. So I'm not saying it cannot be done, but I haven't seen it. So is this work you mentioned? What is this?
So this would be to interest, yes, for background with an ADS factor to analyze those.
And whose work are you referring to here?
No, so I'm mostly working referring to the work that has been done for superstrings. So, for instance, ADS5 crosses 5.
Yes.
And then, so by
But even ADS5 cross S5, it's very difficult to solve the superstring theory in that background, even to do the first quantization. As far as I know, this is of course it's an integrable theory in the sense of Pohlmeier and the very old results on sigma models and the integrability. But I remember I've discussed this with Gleb Arutyunov a long time ago when he was still at my institute, but at some point he told me that this is basically hopeless. So I'm not sure whether he maintains this point of view or not. So, but it's difficult, and it's going to be even more difficult for the membrane.
Okay, thank you very much.
Welcome.
Okay, more questions, please.
Okay.
If no more questions, thanks Hermann once again for very stimulating talk. It is sometimes very useful to listen about a problem which are posed many years ago, and they need a lot of technical effort. Maybe some young people can work in this direction. Okay.
Well, I should say it's I mean, it's certainly challenging, it's certainly worth the effort, but don't expect any quick results. And this is a kind of problem that will take could take decades to solve. So
maybe I will ask last question. Is it possible to use very powerful computers to do some calculations with membrane? What is your opinion about that?
This thing, my result with Lechtenfeld, this is actually something that one could eventually implement on a computer, because some of on my first slide I had these references, and some of those results for super Young Mills theory were obtained by use of a computer-aided technology.
Okay, thank you. Thank you.
Welcome.
Okay.
So have a nice Christmas time.
Oh yes, we have still to do a lot before Christmas, because now it's a time to write a report for the grants. Yes, and application.
Okay, so
okay.
Bye-bye.
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 Thank you very much.
Bye-bye.
And please send me your slides so that I will upload them to the website.
Okay.
Thank you very much.
Bye, everybody. Thank you. Bye-bye. Bye-bye.
Bye.
Bye.